So before we finish today's lecture, I just wanted to give a few comments on TensorFlow. So kind of first of all, where does the name tensor comes from? So tensors are just multidimensional arrays. So for example, I have an array in one direction, this is a vector, then an array in 2 dimensions is a matrix, and then effectively if I add more dimensions than this multidimensional array here, this would just be a tensor. So this is kind of where the name tensor and TensorFlow comes from, and you probably already guessed where the name float comes from. So effectively we already saw before that those neural networks, we can interpret them as a computational graph, and effectively if I take the data here, like this data table here, this data frame, effectively I already talked before, I can view it as kind of pushing this data and having it flow through the graph, and this is exactly why it's called TensorFlow there. And the nice thing about TensorFlow is that effectively once you define the computational graph, everything is really defined for you, so you don't have to worry about the individual computations. Once the system knows what the computational graph is, it can do the computations for you, and it can kind of do them in the best possible way. So effectively you define your computational graph in Python, but underneath the hood everything is implemented in C++, and it can kind of deal with it in the best possible way here. And often to do so I will sometimes have to put in some placeholders. So basically before I actually start pushing the data through, when I define the model, I'm telling the TensorFlow already, well, there comes something of this dimension, build the graph accordingly, and then I will kind of build the computational graph, and then all I have to do for this backpropagation, basically TensorFlow can do that very efficiently underneath the hood once I have given it the computational graph it should use. And that makes it also very simple, so I don't have to really write down this matrix vector multiplications by hand. I could do so, and I should better get the same result out, but what I can do, I can just very efficiently define it in a very compact way. All I'm telling TensorFlow, well, here's a layer of a given size, and then TensorFlow will automatically build the computational graph. And this is even done easier with some wrappers here. So in TensorFlow you still have to define all the kind of weight matrices, what dimensions they are. You don't have to do the multiplication by hand, but you still have to define the weights and the biases as separate objects. If you use like a further wrapper on top of it, like Keras for example, you can see that here you only have to specify something like there's a dense layer of 64 units, and it has a ReLU activation function. Then I have another dense layer with another ReLU, and then I have one output layer. So this will effectively define this network here, where I have kind of my input data, then I have a hidden layer of size 64, another hidden layer of size 64, and then I have one output basically. And this is how you define the whole model. So kind of layer by layer, you just say, okay, here's a kind of input data. Now I have a hidden layer of size 64. This would be the first dense layer object. Then I have the second one here, which is again 64. And then I have this last one, which is basically down to 1 here. Those would be the 3 dense layers here, kind of this one here, and this one here, and this one here, which will be the last one, and this orange one was the one before. So kind of one by one I'm defining this network. Now I have defined the network, I get the output, and then again I don't have to write down how to compute the gradient or everything, because on the computational graph we can do the automatic differentiation, which effectively is the backward forward propagation, which automatically gives us the gradient. And I can just say use the gradient descent optimizer with a learning weight of 0.001, and that's all I have to say basically. And then I say, well, there must be a loss function at the end. What is it? MSE loss, so standard residuals basically, and then I use my optimizer to optimize it, and that's it. Then I define the whole model, and now I just say model fit and model predict exactly as you did in all other sklearn topics, and you can easily build a neural network. So a lot of these details which we discussed today is kind of dealt with for you automatically when you use those packages, and that's why they are so popular in practice.